All right, we continue on today then by continuing to look at the most common kinds of corrosive materials that there are, in particular acids and bases. Now, we spent the majority of Monday talking about acids. How we recognize acids by their formulas, what kinds of things acids do in terms of things like conducting electricity, being able to react with different kinds of materials, and the difference between strong acids and weak acids. We're going to kind of conclude this preliminary discussion of acids by talking about some common acids, things that you've probably encountered somewhere along the line, and whether you didn't realize it or you just didn't know, there are some common acids that play relatively common roles in how we live our lives. So here are some of the most common ones. Nitric acid. Nitric acid is used in a number of different applications. It is a precursor for fertilizers. It's where the nitrates, or at least some of the nitrates, come from in fertilizers. It's one of the places where we get nitrogen. We also get nitrogen from ammonium compounds in fertilizer, which we'll talk a lot more about that when we talk about oxidizers in a couple of weeks. And because of this oxidizing power in the nitrate ion, we actually will see it used in explosives as well. Sulfuric acid. Sulfuric acid is the wet component of a wet acid battery. Wet acid battery that we are most commonly familiar with is the lead acid battery that powers most of our vehicles. And it is sulfuric acid, actually pretty concentrated sulfuric acid, that provides the conducting medium between those lead plates to allow the battery to work. This is in contrast to normal batteries that we usually think of, which are dry acid batteries, where the conducting medium is this paste of sorts that conducts electrodes of different types. In a lead acid battery, you're connecting lead and lead oxides together, and that is what conducts the electricity through that sulfuric acid. As I mentioned before, phosphoric acid is commonly found in sodas. In particular, this is a much more common thing in colas and other brown types of sodas. Those usually have phosphoric acid in them. Your clear and colorless sodas, your Mountain Dews, your Sprites, 7-Ups, you name it, those tend not to have phosphoric acid in them. They tend not to need it. Hydrochloric acid can be found in toilet bowl cleaners. I've made mention and reference to this a number of times. The toilet bowl cleaner known as the Works is the one that uses hydrochloric acid as its primary cleaning agent. And those of you that are familiar with the Works bomb, a do-it-yourself home, not really explosive device, but it's not exactly fun. It's not exactly clean, easy using either. But nonetheless, it works on the chemical action between the hydrochloric acid in the toilet bowl cleaner and the aluminum metal that you ultimately stick into the bottle. There's usually at least one of those stories. I actually had never heard of it before I started teaching this class 8 years ago. And one of the first things that group of students was like, "Oh, do you know how to make a Works bomb?" "No, what is that?" "Oh, you do this and it does that." And it's, "Oh, okay, I know who I'm working with now. I'm going to take a step this way." Oh, and definitely. Now, the the uptick on this one obviously is the gas that is formed that makes all the pressure is hydrogen, and so um, the the most dangerous part of it, obviously, the exploding acid has some fun ramifications, but if you were able to catch the hydrogen on fire as it was coming out, that would also be quite dangerous as well. Um, perchloric acid. Perchloric acid is also an oxidizing acid, like nitric acid is. It is used in explosives. It is used in fireworks for that very reason. The perchlorate ion with those extra oxygens in it is capable of causing other oxidation reactions to occur, to often very significant effects. And then finally, acetic acid, which we talked about before. Acetic acid is primarily found in vinegar. Vinegar is roughly a 5% solution of acetic acid in water. You can find vinegar in some certain types of wines, in particular fortified wines, things that might be used in cooking or otherwise. If you have vinegar in your wine, like good wine, that's actually a really bad thing. That means that the wine has started to turn. Some general properties. Acids are covalent compounds. So even though they have electrolytic properties, even though they will split up into ions when they are in water, they are covalent compounds. They are held together by covalent bonds. So everything that we talked about in chapter 4, in terms of how that is put together, still applies. Hydrochloric acid is a covalent compound. Sulfuric acid, which is a little bit more complicated, is a covalent compound as well. But when they dissolve in water, that bond between the hydrogen and the other element breaks, and we end up getting ions as a result, and that's what allows them to conduct electricity. And so that's where our electrolytic character comes from. It comes from the splitting up of those ions in the water. As most of you know, just on sheer experience, acids do tend to taste sour. How do you know that? Well, you've encountered acids, maybe not these acids on your tongue, but certainly things like citric acid, which is found in lemons and limes, or ascorbic acid, vitamin C, which has a sour flavor to it. The sour flavor associated with citrus fruits comes from the high amounts of acid that are found in those citrus fruits. What was that? I couldn't tell you the exact chemical makeup of a warhead, but I would imagine that if we broke it down, you would probably find some ingredients in there that have that same effect on your tongue and access those receptors on your tongue. Acids will also turn blue litmus paper red, and they will neutralize bases. Bases also known as alkaline substances. Alkaline just is another word for base. When acids react, There are a number of common reactions that they undergo. Acids, for the most part, will react with virtually all metals. There are some exceptions. The exceptional metals are basically what we would call the inert metals. The inert metals are things like copper. Copper does not react with acids unless those acids are capable of oxidizing copper. So hydrochloric acid will not react with copper, but nitric acid, because nitric acid is an oxidizer as well as an acid, will. Silver, gold, platinum, palladium, those tend to be very acid resistant, just in general. They tend to have very, very low reactivities as a general principle. So does mercury. But other than these inert metals, acids do react with metals. So aluminum is vulnerable, magnesium is vulnerable, calcium is vulnerable, all of the alkali metals are vulnerable, zinc is vulnerable. And so there are some cautions that we have to take when using acids around these kinds of metals. Acids will also react with metallic oxides to form salts of metal and water. This is a process known as pickling. This is one of the primary ways that we actually get metal samples from dirt. If you dig up the earth, what you'll find in the earth is a series of organic materials, the dirt, but you'll also find a bunch of rocks. And in those rocks, you're going to find elements like calcium, not in its elemental form, but in its oxide form, where elemental calcium has reacted with the oxygen in the air over time and formed an oxide material. We put that calcium oxide in the presence of some acid, we can get calcium chloride, which is soluble in water and water itself. That is a pickling process that now that we have calcium out of the rock, we've got it just in solution, we can do some other processes to get the calcium out of the water if we wanted to isolate pure calcium. And we can do this for a number of different other substances as well, including some of the more significant kinds of rare precious metals. So if you ever hear of anyone talking about, how we can get gold out of rock, most of the time when we find gold in the earth, it's in its pure form. But there is some untapped amounts of precious metals that have oxidized over time and are just part of, the land. And pickling would be a process by which we could get them out. It's expensive, it's kind of arduous and difficult in times, but it is a possibility. We can also see reactions with carbonates. When acids react with carbonates, they will produce carbon dioxide, water, and some kind of a solid. Probably the most common example of this that you would know is if I have acetic, let's try that again. If I have sodium bicarbonate, which is baking soda, and I react it with acetic acid, the result is water, carbon dioxide, and sodium acetate. Any of you that made a volcano in middle school or elementary school, or did any kind of baking soda and vinegar reaction when you were a kid, this was the reaction that you were making. And it's the carbon dioxide that is generated that causes the whole thing to kind of swell up and blow up as it goes. Because carbon dioxide gets trapped in the water, forms a whole bunch of these bubbles, And if you have a really good way of getting them to kind of pressurize, that's more or less what the volcano reaction is all about, is slowing the build of the pressure enough that it'll cause all of it to come out at the same time instead of just kind of little bit at a time. When it comes to your skin, acids will also react with your skin. The nature of the damage to your skin depends on the concentration of the acid. It also depends in a small part in terms of the duration that the acid is on your skin, which is why when you get acid on your skin in any kind of application, the first thing that you need to do is get it off of your skin, start rinsing your water or start rinsing your hands or whatever part of your body is affected with lots of cold water pretty much as soon as you can. This is going to dilute the acid, which helps, and is going to decrease your exposure. Primary contact will show reddening of the skin at the site of contact, kind of similar to a low-level first-degree burn, where you can find just these little pink red patches on your skin where it has come in contact with you. Prolonged exposure to higher concentrations will actually start to see blistering of the skin. And then finally, even longer exposure, especially with high concentration, can lead to some pretty significant tissue damage and potentially disfigurement of the person, depending upon what part of their bodies are being exposed. So this concludes our mini tour of acids. We're going to come back to acids a little bit at the end, but are there any questions right now? Yeah, go ahead, Michael. Well, so I mean, your stomach is equipped with a membrane that regulates pH pretty well. So inside of your stomach, it's not going to do that much. Now your esophagus and kind of the digestive tract on the way down, yeah, that's going to hurt pretty significantly. And if you didn't do anything about it, then yes, it's gonna cause you some damage. You're probably gonna start bleeding and blistering that spot, that stuff up there as well. Now, chances are, unless you're just incapacitated or something else is going on with you, you're probably going to step in and do something at some point. But yeah, the primary damage would be basically the path from your mouth down to your stomach. Once it gets to your stomach, your stomach's pretty well equipped for that. Your stomach holds a pH somewhere right around 1. So throwing down a heavy dose of acid, yes, it's going to hurt, but it's also, your stomach's equipped for some of that kind of abuse, but the rest of your digestive tract really isn't. So yes, you'd have some significant issues with that. I mean, it's the same kind of thing. If you get sick and you're vomiting, your throat hurts because the acid that's in your stomach ends up in your throat, and your throat's not equipped for that, and it hurts. And it hurts for a while until the skin is able to repair it. But your body's kind of already in defense mode because you're sick. So you're usually doing things to help with that. But no, if you just did that either accidentally or on a dare or something like that, yes, it would definitely hurt. You would want to seek out some kind of a treatment to prevent the damage from getting too bad. And usually in those cases, I mean, that's kind of where poison control comes in too, because chances are the stuff that you're ingesting is also pretty dangerous on its own. All right, other questions? All right, let's talk about bases then. Now, according to the Arrhenius definitions that we are using, bases are substances that are going to give us hydroxide ions in water. And so that is how we recognize them by their chemical formula. We're looking for that OH group in the chemical formula. So things like magnesium hydroxide, sodium hydroxide, ammonium hydroxide. The presence of that OH group there is going to be what allows us to look and say, oh, that's a base. Now, there is one exception to this, and that is the gas ammonia. Ammonia, NH3, is a gaseous substance that has basic qualities to it. Unlike these two up here, which are solids, and when they are when they dissolve in water, basically the magnesium ion and the hydroxide ion split apart from each other. Ammonia's reaction is a little bit more complicated. Like I said, remember, ammonia is a gas. And so when it reacts with the water, it's going to form ammonium hydroxide, which is one of the bases that I give up here. And it's the ammonium hydroxide that will ultimately split into the ions. Most bases are ionic solids, most common bases at least. Now, there are a host of organic bases that are not solid and really have very little resemblance to anything that we're talking about here, but that's a different conversation for a different course. Again, for bases, we're going to primarily look for the presence of those hydroxides or that ammonia group right there. When it comes to bases in their names, their nomenclature is actually pretty easy. Since we're talking most of the time about a metal ion with a hydroxide, the name of the base is just that, metal hydroxide, metal hydroxide. So Mg is magnesium, that's magnesium hydroxide. Na is sodium, that's sodium hydroxide. Al is aluminum, that's aluminum hydroxide. The only one that doesn't follow that pattern, it's the same exception we've been talking about, has been that ammonium hydroxide, the NH4OH. These 6 bases are the ones that you do need to know both in name and in formula. They are that common. Some of these have some pretty interesting uses. For example, sodium hydroxide, most of you probably know it better as lye. If you've heard of lye, if you've heard your grandparents talk about using lye for doing different things, that is sodium hydroxide that they are using. Potassium hydroxide has another common synonym. It's called potash. And we'll get to some other common uses here in a bit. but these 6 are the ones that we really need to know. We generally make bases by taking oxides that are metallic and reacting them with water. So if you remember back to Monday when we started all of this off, we talked about the idea that acids came from non-metallic oxides and bases are going to come from metallic oxides. So metals play a prominent role in these. And so we're looking at metallic oxides reacting with water. When they react with water, we get a hydroxide, lithium hydroxide in this case, and hydrogen gas. And so this actually presents a secondary kind of hazard for these kinds of reactions, since that hydrogen gas is flammable. Common uses for bases: lithium hydroxide is used in lithium-ion batteries. So these are the batteries that power things like watches, hearing aids, computers, laptops, tablets, those kinds of things. Potassium hydroxide, also known as potash, is used in the production of liquid soaps. Sodium hydroxide, also known as lye, is used as an ingredient in making bar soaps. So bases do factor in heavily into the reaction to make soap. Now, when we talked about Class K kitchen fires, I talked a little bit about saponification reactions. And that's where you have the hot fat that you blast with base, and it causes the fat to start to congeal. And that's essentially what's happening in these cases. If you've ever made soap, that's generally the reaction that is going on. You take some sort of fatty material. In the old days, it would be animal fat. Nowadays, it can be a number of different things. But you take that animal fat, you get it to a liquid phase, you boil it, you throw in your base. The base causes those animal fat molecules to congeal, firm up, you press it into a mold, that becomes soap. That is the origin of solid bar soap. Potash reacts slightly differently. The soap that comes out is more liquidy in nature. But if you look at the ingredients, for like a soft soap, so a liquid soap that you'd buy at Walmart, you're going to find that there's usually some kind of potassium hydroxide derivative among the ingredients, because that is how it is made. Also with sodium hydroxide, we have drain cleaners. Drain cleaners like Liquid Plumber, Drano, are a combination of lye and bleach and some other materials. And those materials kind of take care of the majority of the stuff that would gunk up your drain. And they react with it by chemical action. The bleach acts as an oxidizer. The hydroxide acts as a corrosive. And the two in combination usually react away most of the stuff that would cause your drain to be clogged. Ammonia is in the fertilizer area. Anyone that works in agriculture knows that one firsthand. Magnesium and aluminum hydroxides are used in antacids. Magnesium hydroxide is actually something known as milk of magnesia, which has other kinds of properties to it, along with its antacid properties. Aluminum hydroxide is found in Rolaids, and is the primary antacid there. Your more conventional antacids don't actually use hydroxides at all. Most of those use things like carbonates instead. So if you think about your Tums, Tums is probably the most common antacid on the market. And if you look at the ingredients, it's not calcium hydroxide that you're ingesting, it's calcium carbonate. And the calcium carbonate works kind of on the same principle because carbonates react with acids and would neutralize the acids. Overall, bases have fewer properties than acids do. They're a little bit less reactive. But overall, they do taste bitter. Again, think about what it tastes like when you bite into an antacid. They can add all of the mint and fruit flavoring that they want. At the very base, it's still chalky and kind of bitter. Bases on their own feel slippery. That is not necessarily because they are slippery, but it has more to do with they cause a small reaction on your hands, and your hands kind of get a slippery kind of feeling as a result. Like acids, they are capable of conducting electricity because they do break apart into ions in water. The strength of their conductivity depends upon the strength of the base. And finally, these will turn litmus blue. So I've mentioned litmus twice now. Litmus is a chemical indicator that basically comes in two colors, red and blue. When litmus encounters an acid, it will turn red, which means if I have red litmus paper already, it's going to stay red. If I have blue litmus paper, it'll turn the blue litmus paper red. Bases will turn the red paper blue and keep the blue paper the same. Substances that are neither acid nor base won't change either of the strips. And that's how we know that they're neutral. One of the things that sets bases apart as different is their ability to exist in the solid phase. Most of the acids that we encountered were gases first, or only existed once some kind of a gas dissolved in water. So this one on the left here, this is actually potassium hydroxide, KOH. Comes in those little pellets. Sodium hydroxide actually has a similar appearance, but it also can exist in flake form, as is shown here. This last one here, baking soda, is not a hydroxide at all, but rather a carbonate derivative, sodium bicarbonate. And as I mentioned before, carbonates do have basic properties, even though they are not hydroxides. So they're good at neutralization, but they're not really caustic. You know, you put baking soda and you spill baking soda all over your hands, it's not going to cause a chemical reaction with your skin. In fact, we kind of use it in the opposite direction. We use baking soda to help us clean up and neutralize acid spills. So if you get a good spill of acid on your hands, one of the things that we do in the lab is we pour baking soda solution over your hands to help neutralize that acid as you're washing your hands, so that we can negate that chemical action as quickly as possible. Now, bases can exist in liquid and gas phases as well. Common example of that is ammonia, but it's far less common. those those bases that are in the liquid or the gas phase are far less common than the solid phase ones. We can classify bases based on strength, just like we classified acids. Strength of a base and strength of an acid are evaluated in the same way. It's all about ionization power. So for a strong base like sodium hydroxide, what we see is complete conversion. All the sodium hydroxide molecules turn into sodium ions and hydroxide ions. That 100% ionization is really important. That means that we're going to have lots of ions available. We're going to have strong conductivity as a result. Weak bases do not do the same thing. Weak bases, we tend to see the majority of the material, even though it is dissolved, stays undissociated, stays as a molecule. And so we do see conductivity. We still do have ions present, but that conductivity is relatively weak. But both solutions of weak acids and strong acids, weak bases and strong bases, they will conduct electricity. They will just conduct it varying based upon how many ions are there. When it comes to reactions with metals, we see that bases will react with 3 different types of metals. They will react with aluminum, they will react with zinc, and they will react with lead. End of list. Notice also that the reactions themselves are only with strong bases. So we saw with acids, we could use diluted solutions of really kind of any acid, but strong acids in particular. Here we need concentrated solutions and strong bases. That's the only way that we get these reactions to actually run the way that they're supposed to. All right, this is where we're going to call it a day. On Friday, we will finish up by putting the last touches on bases, and then we will talk about the kind of thing that draws them all together, and that is the pH scale. Have a great afternoon.